There's so much nonsense out there about batteries, you can believe about 1% of what you read. Lithium-ion covers a very broad range of technologies. An enormous difference in the power density and the energy density and the cycle life between one chemistry and another. They can be really enormously different.
Imagine a battery that outlives you, your children, and possibly your great-great-grandchildren. Not by years, but by millennia. While your smartphone dies before dinner, scientists have cracked the code on power sources that could run for 28,000 years.
The NDB Universal Self-Charging Battery provides a charge of up to 28,000 years of battery life.
And they're aiming to put them in your hands by 2026. What exactly are nuclear diamond batteries? The concept sounds like science fiction, but the physics is surprisingly straightforward. Take carbon-14, a radioactive isotope that naturally occurs in our atmosphere. Now, trap it inside a synthetic diamond. That's essentially what nuclear diamond batteries are. Here's how it works. Carbon-14 atoms undergo beta decay, meaning they slowly release electrons as they transform into nitrogen-14. This process happens continuously and predictably over thousands of years. The diamond casing does double duty. It contains the radiation safely while also converting those beta particles into electricity through a process similar to how solar panels convert light into power. The power density is incredibly low compared to conventional batteries. We're talking microwatts, not the watts your phone demands. But here's the kicker: it never needs charging. The carbon-14 has a half-life of 530 years, meaning after nearly 6 millennia, your battery still operates at 50% capacity. The synthetic diamonds used aren't the sparkly gems you'd find in jewelry. These are industrial-grade diamonds, grown in laboratories using chemical vapor deposition. They're incredibly hard, making them nearly indestructible, and they're transparent to the beta particles being emitted. This transparency is crucial because it allows the particles to interact with the diamond structure, generating electron-hole pairs that produce electric current. Think of it as a tiny nuclear reactor wrapped in the hardest natural material known to science. The carbon-14 sits in the diamond lattice itself, meaning the radioactive material and the protective casing are one and the same. There's no risk of leakage because there's nowhere for the material to leak from. The long journey. From lab concept to reality. The idea of using radioactive decay for power isn't new. Scientists have been playing with this concept since the 1960s. Early radioisotope thermoelectric generators used plutonium-238 to power spacecraft like Voyager 1 and 2, which are still operational after launching in 1977. But those systems were massive, expensive, and definitely not something you'd want in your pocket. The diamond battery concept specifically emerged from research at the University of Bristol in the early 2010s. Researchers were looking at nuclear waste from graphite blocks used in old nuclear reactors. These blocks had absorbed significant amounts of carbon-14 during operation, and disposing of them was proving expensive and complicated. Someone had a clever idea. What if this waste could become a resource? The team discovered that by processing these graphite blocks and converting the carbon-14 into diamond form, they could create a battery that was both safe and incredibly long-lasting. The diamond structure was key because it could contain the low-energy beta radiation while simultaneously converting it to electricity. Throughout the 2010s, the technology remained mostly theoretical. The power output was too low to be practical, and manufacturing processes were prohibitively expensive. Creating synthetic diamonds with the right isotopic composition and structure required precise control that was difficult to achieve at scale. The breakthrough came when researchers realized they didn't need pure carbon-14 throughout the entire diamond. A thin layer of carbon-14 sandwiched between layers of non-radioactive diamond would work just as well while using far less radioactive material. This multi-layer approach dramatically reduced costs and simplified manufacturing while maintaining similar power output. By 2020, multiple research groups worldwide had demonstrated working prototypes. The race was on to make them commercially viable. The 2024 to 2025 breakthrough moments. Two major advances in the past 2 years have transformed nuclear diamond batteries from laboratory curiosities into commercial products. The first involves manufacturing efficiency. Companies have developed new techniques for growing diamond layers that are thinner and more uniform than ever before. We're talking about layers just a few micrometers thick with precisely controlled carbon-14 concentration. This precision matters enormously. Too much carbon-14 in one spot and the radiation self-absorbs before it can generate electricity. Too little and you don't get enough power output. The sweet spot requires manufacturing tolerances that were simply impossible to achieve economically until very recently. Advanced chemical vapor deposition systems, originally developed for quantum computing applications, have been repurposed for diamond battery production. The second breakthrough relates to power output. Early prototypes generated just a few microwatts per gram. Recent designs have pushed this to 15 to 20 microwatts per gram, with some experimental versions reaching even higher. That might not sound like much, but it's enough to power a wide range of low-power electronics indefinitely. Safety certifications have also fallen into place. Regulatory bodies in the United States, Europe, and Asia have established frameworks for handling and transporting these batteries. The radiation levels are genuinely minimal. The beta particles from carbon-14 can't even penetrate human skin, and the diamond casing provides multiple layers of protection. Testing has shown that even if you crushed a diamond battery with a hammer, the radiation exposure would be less than you'd get from eating a banana. Manufacturing costs have dropped by roughly 80% since 2022. What once cost tens of thousands of dollars per unit now costs hundreds, with projections suggesting prices will continue falling as production scales up. Companies have also solved the connection problem. Getting electricity out of a tiny diamond efficiently was trickier than you'd think, but new metallization techniques allow for reliable electrical contacts that don't degrade over decades. Who's actually making these batteries? Several companies and institutions are leading the charge toward commercialization. The University of Bristol spin-off company, in partnership with the UK Atomic Energy Authority, has been at the forefront. They've developed a process for extracting carbon-14 from nuclear waste and converting it into battery-grade material. California-based NDB Inc. announced plans for commercial production in 2024, claiming their batteries could provide power for up to 28,000 years depending on configuration. They're focusing initially on specialized applications where replacing batteries is expensive or dangerous, like deep-sea sensors and space applications. In Asia, several research institutions have joined the race. China's BetaVolt has demonstrated prototype batteries and announced ambitious production timelines. Russian researchers have also published promising results, though their commercial plans remain less clear. The involvement of established nuclear energy companies has legitimized the technology. These organizations bring expertise in handling radioactive materials and navigating regulatory frameworks that startup companies often lack. They also have the capital to build specialized manufacturing facilities. Interestingly, some diamond manufacturers have entered the space. Companies that previously focused on industrial diamonds for cutting tools or semiconductor applications are now pivoting toward energy storage. They already have the equipment and expertise for growing synthetic diamonds. Adding radioactive isotopes is a logical extension of their capabilities. The supply chain is gradually taking shape. Carbon-14 production is the bottleneck. While some can be extracted from nuclear waste, most will need to be manufactured in nuclear reactors specifically for this purpose. Several facilities are being upgraded or built to meet anticipated demand. What could you actually power with them? Let's be clear about limitations up front. You won't be charging your smartphone with a diamond battery anytime soon. The power output is too low for high-drain devices, but for applications where longevity matters more than peak power, these batteries are revolutionary. Medical implants are the obvious first target. Pacemakers currently last 7 to 10 years before requiring surgical replacement. A diamond battery could potentially last a patient's entire lifetime. The same applies to other implanted devices like neurostimulators, drug pumps, and biosensors. The cost savings and reduction in surgical risks are substantial. Remote sensors are another perfect application. Imagine environmental monitoring stations in the Arctic, deep ocean sensors, or wildlife tracking devices that never need battery replacement. Currently, maintaining these sensors costs millions in helicopter flights, ship deployments, and technician time. A 50-year battery life changes the economics completely. Space applications are particularly promising. Every gram launched into orbit costs thousands of dollars. A battery that provides reliable power for decades without replacement is enormously valuable. Small satellites, Mars rovers, and deep space probes could all benefit. NASA and other space agencies are watching developments closely. Consumer electronics will come eventually, but with different use cases than you might expect. Think of devices that require tiny amounts of power over long periods. Smart home sensors that monitor temperature, humidity, or air quality could run indefinitely. Emergency beacons, smart locks, and RFID tags are all possibilities. The military has obvious interest. Soldiers carry heavy battery packs that need frequent recharging or replacement. While diamond batteries can't replace those high-power systems, they could power auxiliary equipment like GPS trackers, communication devices on standby mode, or sensors built into equipment and infrastructure. The 2026 timeline, what to expect. Why 2026 specifically? The date reflects realistic timelines for scaling production and completing regulatory approvals. The technology is proven. Now it's about manufacturing capacity and navigating bureaucracy. Throughout 2025, expect to see limited production runs for specialized applications. Early customers will likely be space agencies, military organizations, and medical device companies willing to pay premium prices for proven reliability. These early adopters help manufacturers refine production processes and gather real-world performance data. Regulatory approval processes are already underway in multiple countries. The International Atomic Energy Agency has published guidelines for diamond battery safety and transport. Individual nations are adapting these guidelines into specific regulations. The United States Nuclear Regulatory Commission is reviewing applications, as are equivalent bodies in Europe and Asia. By late 2026, initial commercial products should reach market. Don't expect to buy them at your local electronics store. Initial distribution will be through specialized channels to industries with existing frameworks for handling radioactive materials, even ones as safe as these. Pricing will be high initially, perhaps $500 or $1,000 per battery depending on specifications. But costs should drop quickly as production scales. By 2028, prices could fall to $100 or less for basic versions, making them competitive for many applications when you factor in their multi-decade lifespan. The biggest uncertainty is public perception. If media coverage focuses on nuclear batteries without context, public fear could slow adoption regardless of actual safety. Companies are investing heavily in education and outreach to prevent this. The elephant in the room, safety and radiation concerns. Let's address what everyone's thinking. Nuclear anything makes people nervous, but the radiation from these batteries is genuinely minimal, and here's why that's not just marketing spin. Carbon-14 emits beta particles, which are essentially electrons traveling at high speed. These particles have very low penetration power. They can't pass through the diamond casing, they can't penetrate human skin, and they're blocked by a sheet of paper. The diamond encapsulation provides multiple layers of redundancy. To put the radiation in perspective, you receive more radiation exposure from sleeping next to another person for 8 hours than you would from carrying a diamond battery in your pocket for a year. Bananas emit more radiation due to their natural potassium-40 content. A cross-country flight exposes you to more radiation than a lifetime of using diamond battery devices. The half-life issue also works in favor of safety. Carbon-14's 5,730-year half-life means it decays very slowly, which translates to low radioactivity. Fast-decaying isotopes are dangerous because they release lots of radiation quickly. Slow decay means minimal radiation at any given moment. Containment is foolproof by design. The radioactive material is literally trapped in the crystalline structure of the diamond itself. There's no container that could crack open. Even if you somehow ground the battery into powder, the carbon-14 remains locked in diamond particles too small to pose any inhalation risk, and the radiation still can't escape. Independent testing has verified these safety claims. Batteries have been subjected to crushing, heating, immersion in water, and other stress tests. In every case, radiation levels remained below background environmental radiation. Why this changes everything and what it doesn't. The environmental impact alone could be transformative. Billions of batteries end up in landfills every year, leaching toxic materials into soil and water. A device that needs one battery for 50 years instead of hundreds over the same period represents a massive reduction in waste. Remote infrastructure monitoring becomes economically viable in ways it never was before. You could embed sensors in bridges, pipelines, and buildings that report structural health continuously for decades without maintenance. Early detection of problems could prevent catastrophic failures and save lives. The developing world benefits disproportionately. Regions without reliable electricity grids could deploy sensors, communication devices, and medical equipment that doesn't depend on charging infrastructure. A medical clinic in rural Africa could have equipment that runs indefinitely regardless of power availability. But let's pump the brakes on the hype. Lithium-ion batteries aren't going anywhere. Your laptop, phone, and electric car need high power output that diamond batteries simply cannot provide. The energy density is orders of magnitude lower. These technologies serve different niches. The impact will be more subtle than revolutionary. Devices you rarely think about will quietly stop needing battery changes. Infrastructure you don't see will become more reliable. Applications that were previously impractical will become feasible. But you'll still plug your phone in every night. Cost considerations will limit adoption too. Even at $100 per battery, many applications can't justify the expense when disposable alkaline batteries cost $1. The economics only work when replacement costs are high or when extreme longevity is required. The technology also has physical limitations that aren't going away. Power output is fundamentally constrained by the decay rate of carbon-14. You can make batteries bigger to get more total power, but power density remains low. Some applications will always require different solutions. Still, witnessing the birth of a new category of energy storage is rare. Most of us will never again see a genuinely new battery technology go from laboratory curiosity to commercial product. The first devices powered by decay that began thousands of years ago and will continue thousands of years into the future are coming soon. Whatever your smartphone is doing in 2026, somewhere nearby, a tiny diamond will be quietly generating electricity from the fundamental forces of nuclear physics. And it'll still be doing exactly that long after everything around it has turned to dust.